Welcome back. This is our week 8 of graduate statistic. Again, it's blowing my mind that we are on our 8th week already. Anyways, previous video, I wanted to introduce you formally to the t-distribution. And we said we use the t-distribution when we cannot reconstruct the sampling distribution of the mean under the null hypothesis using the z-distribution because the conditions for applying the central limit theorem does not hold. In particular, we can't estimate the variance because we have a smaller sample size. And I also told you that the t-distribution differs from the z-distribution in that it has thicker tails. And the tails will be ever more thick, ever thicker if sample size is smaller and smaller. So for smaller sample sizes, the tails will be very thick. If I increase sample size, the tails will reduce, all the way up to making the t transform back into a z distribution. Because if the population is large enough, then t and z are just the same. All right? Now, I asked you to illustrate this. I showed you that the consequence of thicker tails is that you will need a statistic that expresses a greater deviation of your observed mean from the null hypothesis mean in order to reject the null hypothesis. To make this concrete, I showed you that if you got a statistic of 2 and it's a z statistic, and you used p-norm to get the probability of finding that value or more extreme in either end, two-tailed test multiplied by 2, is 0.04, and you would reject the null hypothesis then. If it was a 2 and you're looking at the probability of finding 2 on a t-distribution of only 9 degrees of freedom, you would not reject the null hypothesis. So you would need a greater deviation for rejection if you had a sample size of 10 and you only had 9 degrees of freedom. Okay? All right. Now let's get to examples. Playing a computer game during lunch affects fullness, memory for lunch, and later snack intake. That's the name of the study. That study included 22 participants, so a small sample size, 11 men and 11 women. And in that study, participants played solitaire while eating, so they were distracted while eating. They were told to win as many games as possible. Later, they were offered biscuits and their intake was measured. These are the summary statistics. Let's describe the data. Here is, the participants played solitaire and they were offered biscuits and they ate 52.1 grams on average. That's the average intake. That's the X-bar intake, the observed in the sample, right? There is a true average if everybody in the population were distracted and then were offered biscuits. But we're trying to estimate that true average with our sample average, the X-bar. The standard deviation of the sample was 45.1. And we looked at 22 people. Oops. Now, we have some questions to answer here. Question 1. What is the average snacking level for distracted eaters? So they were distracted. We looked at their consumption of snacks that were offered to them, in particular biscuits, and now we want to know what's the average. And does distraction during one meal modify the amount of food consumed later for a snack? Okay, so imagine we have these two questions. Let's address the first one first. Again, we have the summary statistics here, and we can say, oh, the average snacking level is 52.1 grams. So I'm answering that with some variation. Now remember, 52.1 is a point estimate of what the snacking amount would be for people that get distracted during eating. I'm trying to estimate that, about the population at large, making an inference that people will eat about 52 grams of snack after being distracted during the prior meal. Okay? Remember, point estimates are limited because we rarely ever get them perfectly right. So what can we do in addition to a point estimate to answer question 1? Is to compute a confidence interval around it, right? So what is the average snacking level? Estimating a population parameter, here the means, entails also a confidence interval. So we could throw a net to get a certain, to increase our confidence level at the estimation of that parameter in the population from sample data. And you already know that confidence interval is the point estimate, say the mean, plus or minus some margin of error, which we computed for the z distribution, right? Now we're going to compute that margin of error considering the t distribution instead. So instead of having x bar plus or minus the z critical, the z that would draw our margins of interest, times the standard error, we will have the t critical in order to compute the confidence interval. And again, the standard error equals the standard deviation of the sample divided by square root of n. And the degrees of freedom for the t statistic for inference on one mean, we just have one mean here, right? What is the mean amount of snacking that happens in the population when people get distracted on a prior meal? So we have 1 degree of freedom. The degree of freedom is n minus 1. We know that our n is 22, so our degree of freedom will be 21 for getting the t critical. So t will depend on degree of freedom and the confidence level that we want, the t critical. So if we want 95%, we want the t critical that draws 2 rejection areas, 2.5 on one side, 2.5 on the other side. So we would use the margins of 2.5 and 97.5 to get the t value. Either one would work because they are the same in absolute terms. So once you get the t critical, you can just plug in the values and compute the interval. That is what we're going to do next. So estimate the average after lunch snack consumption in grams of people who eat lunch distracted using a 95% confidence interval. So let's do that. Here's biscuit intake. We have all the parameters that we need here. We're going to check assumptions for computing confidence interval with t-test. Independence of observations. Distribution should be nearly normal. And large sample. We have this thing, and we don't have this, so we can't use z. So sorry, first you check assumptions to see if you can use the z distribution. You can't because the sample is not large enough, but we can use the t distribution because these other two things are indeed true. And we're going to use the t distribution with 21 degrees of freedom because it's 22 minus 1. So first thing, we want to get the t critical using qt function. So we're going to put one of the margins here. Remember, I'll go back. We need either this one or this one, and the absolute value of t is the same. I tend to use the larger one just to get the positive value. So our critical value, our critical boundaries will be 2.08, and then we can get the interval. Remember, it's x bar plus or minus the t critical that sets the boundary that we want for the confidence level that we wish, times the standard deviation divided by square root of n. So it's just plugging in numbers. So 52.1 plus or minus the t critical that we just computed times the standard deviation divided by square root of n. So here is the confidence interval. You'll be glad to know that you won't have to apply this formula in detail because the t-test function already spits out the confidence interval that we want. So I just want you to really get things conceptually here, that we're doing the same thing as before, except the critical value that sets the boundaries for the confidence interval is coming from the t distribution, not from the z distribution. But it's virtually the same thing we're doing here. That's why I keep saying that I think last class is the hardest, because now it's kind of reapplying the concepts over and over again across a variety of distributions. Okay? So how do we answer this question? What is the average snacking level for distracted eaters? To answer this question, we can say we're 95% confident that distracted eaters will consume between 32.1 to 72.1 grams of snack post meal, right? So we're giving an average with a confidence interval instead of just saying, oh, it's 33 point something, 35 point something. So question number 2 that we have, does distraction during one meal modify the amount of food consumed later for snacks? So here we're just saying distracted eaters will eat this amount with 95% confidence. Is this amount greater than for people that didn't get distracted on the prior meal? So that's a different kind of question we're asking. We're asking about differences between means. Mean snacking, comparing a distracted and a not distracted populations. Okay, so to answer this question, we need a basis for comparison. That's my point. One possibility, which is not the best, but it's one possibility, we can use, if we just have one sample of distracted eaters, is to use the suggested serving size of the biscuits. Do people eat more than the suggested serving size? Assuming that, in general, people will eat the serving size. Iffy assumption, but let's assume that as a starting point, that if people in general in the population would eat the serving size, do people that get distracted on one meal eat more than the serving size on the next meal? So suppose the suggested serving size of these biscuits is 30 grams. Do our data provide convincing evidence that the amount of snacks consumed by distracted eaters post-lunch is different than the suggested serving size? I want you to take a second, and with what we have right now, can we already say with some confidence that it is different? If you're thinking yes, and you're thinking yes because 30 grams is not contained on this interval here, good for you. That's a quick and dirty way to test hypothesis. It's a two-sided hypothesis, so 95% confidence interval is a good one, because on a two-sided hypothesis, I have 95% non-rejection in the middle and 2.5 in each side, so it coincides with the 95% confidence interval. And I'm not seeing 30 inside of here. And the lower value here that's closest to 30 is already 2 grams above. So it's not very typical to see a value of 30 grams, let's say, right? It's not very, so 30 grams is not contained, it's not a typical value for that population. So quick and dirty, we would say, yep, it seems to be different, right? It seems to be different in terms, so we can conclude that when people get distracted on one meal, they will eat more than the suggested sample serving size of snacking. Doesn't really get fully to this question, only if we can assume that the general population will eat the serving size, which is iffy. So when we get back, we'll test this hypothesis more carefully. First, with this assumption that serving size reflects what the population eats, and then we'll do a better way of assessing this particular question. All right, see you in a bit.